Hello, everyone. Welcome to the talk about how game DevOps made easy with AWS Game Server CI/CD pipeline. Together with me, I have Nilam Kushia, and my name is Yahav Biran. We are both a solutions architect in AWS. Let's start with a quick introduction of what we're going to do. Now, if you look at game developers or game publisher, typical game publisher, there are two core personas. The first one are the marketing, the developers that wants to basically develop the coolest game they can do and make it available to their players as soon as possible. On the other hand, you have the CSOPs and the DevOps people of the world who care about reliability, availability, and security. Now, this type of persona wants to make the system more stable, as opposed to the other persona who wants to induce this chaos through these changes. So, how you reconcile these two models? CICD comes exactly to solve those things. It's a set of operating principles and practices that enable developers to deliver code more frequently and reliably. Now, it focuses on both security and quality. Now, it all sounds good in theory, but we heard from our gaming customer that CICD did not work for them as expected. Now, we're going to talk about those difficulties and provide some solutions that will help those things. But in general, building and integrating games involved with many components like the game engine, the third-party packages, and essentially your game. Now, building such game and integrating all this as an image can take a lot of time. It can be tens of minutes, and sometimes it can take hours. So customers specifically told us that sometimes they basically spend most of their half day until noon just building stuff without seeing the value. So we're going to see how to solve those things.
Well, the question on your mind would be how CI and CD can help my game. The most important aspect is to keep the players engaged and have them coming for more by releasing new features to your game. CI and CD not only helps you to release more features more frequently, but also increases the developer velocity. You can continuously build an immersive, ambitious experience to keep the players playing and stay engaged, which is our first goal, to increase game feature velocity by reducing the time to deliver. We also want to keep everyone informed. And let them know about the latest status. So the different personas that Yahav talked about, the artists, the testers, the creative folks on the team, no longer need to follow up about the release status. Once the developer says the feature is complete, it is up to the pipeline to tell the status. In our example, we are going to use Slack, and we'll see more about it in our session today. The third point is CI/CD helps to define and manage set of configurable dedicated game servers to build a consistent and a standardized workflow. For instance, we help to minimize the time it takes to onboard a new team member. No need to set up new LDAP groups for specific tools or services you use. Stakeholders only use a single tool. If I'm an artist or a tester or a business analyst, here is the visibility into what's happening in production. There was a code commit, which was done by Yahav, and he modified the graphic quality. It also lists the game's service specification. As we mentioned, we are using Slack in this example, but this can be easily integrated with any other channel that you have. Now, this all looks very complex and interesting, but we are going to make all this simple and easy and allow you to build an excellent game. But first, let's see our proposed architectural blueprint. So here is the proposed architecture for our game CI/CD. It is broken down into two parts, the CI and the CD. Game developers merge or push the changes into Git repo that includes game engine binaries and game artifacts. Each merge event triggers a Docker image built, which is tested and pushed into the registry. With the newly built images into the registry, Flux CD takes over from there. What is Flux? Flux is a GitHub operator that runs in the cluster and watches for new image in the ECR. When Flux notices that a new image has been pushed to ECR, it checks out the corresponding manifest file, updates it, and then checks it back into Git. After which the new image is automatically deployed to the cluster, updating the game server and maintaining its state against the source of truth, which is kept in Git. Now let's discuss more about CI part of the architecture and flow. Well, let's talk more about CI. Why do we need CI for games? So let's start with the why question. If you look at the daily changes, they are in the order of KBs, kilobytes, then why build the entire server if only a small fraction has changed? The time it takes to build the entire game is long and wasteful. If you multiply it with the many Git pushes and merge requests, it would only amplify it. A developer and a tester shouldn't really have access or even knowledge of how to build and integrate the game binaries. Why not abstract that out? Now that we have the why answered, let's look at what is the main issue here. Let's begin by asking, what is the main issue with continuous integration for game? Game server comprises of game engine, third-party tools, configuration, and game binaries and assets. Let's look at the typical game engine. The size of Lumberyard is 6 gigabytes. Unreal 10 gigabytes, Unity 11 gigabytes. These are in a magnitude of gigabytes. Game engines are typically owned and updated by a different team or even a different organization. Same goes for the third-party tools that we use for our game. So why we are bounding it together with our game, and how can we streamline our integration process such that changes in those components are seamlessly integrated and tested with the game? Let's see how.
Until now, we discussed we got an overview of what is and why, and now we're going to talk about how CI and CD going to help your game, right? So, and as Nila mentioned, game server comprise of, broadly speaking, the game engine itself, third-party tools that sits on top of the that uses the game engine. The game engine libraries, and then on top of that you have the configuration and eventually the games and assets that you build. Now let's look carefully into each artifact type. The goal is to look at the artifacts from ownership and update frequency perspective. So for example, if you look at the game engine, and I'm talking about the stable version, is updated once a month in a really high frequent case, or sometimes every 6 months. And the third-party tools also have different cadence. So as Nila mentioned before, there is no real reason why we need to bound those things together. Now the second part is your game developer needs to integrate the changes and create build, right? Now your game tester wants to know if the game passed some basic tests before delivering the game to further test, right? So because you don't want to end up in a situation where you push the game and then you waste the tester time. So you want to have some sort of automated tester to filter out the obvious cases. And last, we want to discuss the security scenario. So let's say that one of your developer used a package, a third-party package that simplifies something for the development process. Now, assume that this package is infected with some software that mines that runs some Bitcoin miner, right? Image scanning can help mitigate this risk, right? So if you think about it, we are looking at this pipeline from the development all the way to the integration part, and we're trying to optimize those bottlenecks. Now, and this is a basically more specific continuous integration architecture. So if you think about the reference architecture blueprint that Nilam provided, we're going now dive deeper into the continuous integration pipeline. So if we're going to take and separate the three core components, remember, game engine, the third-party tools, and your game, and we pack each separately and stage it in a dedicated Git repository. In our example, we're going to use AWS Code Commit. It's just because it's easier from management of large files, but GitHub is perfectly fine as well, as long as you enable LFS support. Now, what we're going to do is that we're going to kick a process, a continuous integration process that will start upon pushing or merging of a change. Now, also, we are going to build or rebuild, I should say, only the component that was updated in the last change and use the cached layers of the other parts. Finally, we integrate the result as an image with the same caching protocol, and the protocol is Docker. And when we're distributing it globally to the other, to the actually hosted sites, the clusters, we are going to use the same mechanism by using those caching things. So we're not going to actually push those the components that were not changed. But we're going to talk about that in greater details in the CD, the continuous delivery portion.
Great. So let's look at the code structure. So, we have a high level overview of, how it's going to look like, but let's look at how the repository will be looking like and how would be my code. If I'm a developer, I'm worried about how the code would look like. So here is an example of Git repo structure, which is your code basically of the CI source control. Now, if you look at the image which is in the slide, it is of code commit. So code commit is the Amazon's code repository, which integrates with Git. There are 5 major components, and I will go over each and every component. So the first one is the game engine binary. In this particular example, it is the bin Linux 64 dedicated zip file. This is a compressed version of the game engine artifact that are not updated regularly, and hence they are deployed as a compressed file. The maintenance of this file is usually done by a different team than the developer working on the game title itself. The next one is the game binary, which is your code, and this is the multiplayer sample in this particular example. This directory is maintained by the game development team and maintained as a standard multi-branch repository. The artifact under this directory gets updated on a daily or a weekly basis depending upon the game development plan. The third component is the build-related specification. For example, the build spec.yaml and the Docker file. These files specify the build process. For simplicity, I have only included the Docker build process to convey the speed of the continuous integration. The process can be easily extended to include the game compilation and link process as well. The fourth aspect is the Docker artifacts, which is used for containerizing the game engine and the game binary. In this particular example, we have the start.sh and the start.python file. These scripts usually are maintained by the game DevOps team and updated outside of a regular game development plan. And the last one is the deployment specification. In this example, we are going to have the Kubernetes game server deployment spec. And if you look at the slide, it is denoted by the EKS-spec. This is for reference only, since the CD process usually runs on a separate set of resources like staging EKS cluster, which are owned and maintained by a different team. Now let's see the build spec.yaml, which is in the multiplayer sample folder. The build process typically starts with any git push event that happens on the Git repository. Now the build process includes 3 core phases: pre-build, build, and post-build. So if you look at the example that I have on the screen, in the pre-build phase, what happens is you unzip the game engine binary, log it into the container registry to prepare. In our case, the container registry is the Amazon ECR. The build phase executes the Docker build command that includes the multi-stage build. And the post-build phase pushes the game Docker image to the centralized container registry for further deployment to the various EKS cluster. Now in this phase, what you do is you tag and you push the new image to the designated container registry in the ECR. Here we use code build to execute the build script, but we can easily extend this to Jenkins slave if we choose to do so. We rely on Docker multi-stage image And let's see what Docker multi-stage image is and how we are using it for our CI process. Now, this is the secret sauce. We rely on Docker multi-stage build. With multi-stage build, you use multiple from statement in your Docker file. Each from instruction can use a different base, and each of them begin a new stage of the build. You can selectively copy artifacts from one stage to another, leaving behind everything you don't need in the final image. Now, if you look at the example that we have, for simplicity, we are going to use the Lumberyard's multiplayer sample, but other popular game engines also offer the containerization samples. You can feel free to use those. Here we can see the 3 layers, which I have highlighted. The first holds the game engine binary, which is game_engine_linux_bin. The second one holds the third-party tools denoted by qtlibs. Finally, we have our game, which is denoted by the multiplayer sample. You can see how this can be used to describe the build system. This entire thing, the entire mechanism, is called as the Docker multi-stage image. Now let's see a demo of how this all works together.
Awesome. Let's see. So we're going to start with looking at the source, right? The things that Nilam talked to you about. So this is the multiplier sample, the CI repository, right? And here we are going to have the build project, right? In here we have a build process that includes many things, and as you could see here, it is logging all the changes that was made in the past. And in the pipeline here, that's code pipeline, that's basically the orchestrator. The code pipeline is basically Jenkins master that or the code pipeline in the native AWS solution that basically capture the steps. So it's going to start in this case with downloading the source from the Git repository, build it, and push it to the image registry. Let's see all this thing in action. So we are in this code registry. Now, before we start, let's just make sure that we are clean. Yes, so it is clean. So we're going to first of all create a change, make a change in the game. So in our example, I'm just gonna change the graphics quality of the server. I'm gonna change it to 0, which is auto, right? So I'm just gonna store it, and then I want to create a new game, a new image out of it, right? So I'm gonna have to call it, so I'm gonna tag it as version 12, for example, right? So I'm going to do git status. You see that these are the 2 things that got changed. I'm gonna do add git commit -m set to auto, and I'm going to push it. Okay. So now the game has been pushed, right? So if I'm going to start my Slack channel, right? I am going to get a notification as for the change that was made, but I can also, while these things happen, right? I can see all the changes that was made, and here I can gonna go to the pipeline. As you can see that the pipeline, the GDC CI demo, is now in progress, right? It was started and it is doing something, and basically it is downloading now downloading the game, right? If we want to see more details, we can look at the build project, right? And look at the current execution. Can look at all the steps that were done. Since it is now only downloading the code, it didn't start the build, right? But the build going to start once that this step is over, right? Now on the Slack case, we can see all the notification, right? That happened, and I'm usually, as we can see here in the pipeline, you could see that the changes that are made are taking, if I'm looking at the history, are taking between 9 minutes, 8 minutes, right? So we're not going to stare at the screen for 8 minutes. So I'm going to pause now. I'm going to continue with this presentation, and we're going to when we're going to go through the demo of the continuous delivery or the continuous deployment, then we will follow up on the change. But before we do that, I want us to take a look at the previous execution that I did. It was on April 13, as you could see, and let's look at that. Okay, so you could see there was 2 steps. One is the source and one is the build. The build is the one that is the interesting part, is the interesting part here. Now we could look at it from the code build perspective. You could see here that that's the execution, and you could see basically the entire log. We can just go and look at the end. And this is the interesting thing here, right? You could see that, I mean, I'm not going to go through all the changes that was made, but as you could see, there are in the build process, the caching detected, the multi-stage detected that the layer already exists. And if we look at layers that was detected, these are the layers that are marked with no operation, right? And those are the layers. Those layers are not that significant. But if we look at this one, this is the interesting part, right? One here, right? Because there was a 3.04 gigabyte that we didn't even touch. Why? Because it simply was not changed. So that's the demonstration of how we are implementing the caching in action.
Thanks, Yaha, for showing the CI demo. While that's in works, let's look into the second half of the architecture, which is the CD. Now, this is a high-level architecture of the CD process. The CD system comprises of 3 components: the game image that we build, the CD source control that holds the game server profile, and the hosting platform, which is the EKS in our case. Now we start by deploying the EKS cluster we need, for example, per region, per game, depends on the needed scale, player latency, and more. And then we deploy the game profile. The profile includes the artifacts that specify to EKS what to deploy, how to deploy. For example, use the image from ECR, allocate EC2 instance type using Spot or on demand, open the necessary ports, and launch the game. Now let's dive deep into the CD data flow. So let's start with the first part of the puzzle, which is what is game profile. Now a game profile includes all the Kubernetes artifacts needed for successful game hosting. For example, how to start the game server, what is the parameters, the environmental variables, the libraries which is required to link. What about the CPU, the memory, the network resources? What about the EC2 instance? What should I use? Should I use C5-4X large? Should I use C5 large? What should I prefer to use on demand, or go with Spot instances, which provides up to 90% of the saving over the on-demand price, and maybe have a graceful way to handle the interruption with 2 minutes warning? What about the monitoring and the alert configurations, like what matrix should I write to CloudWatch, or maybe Grafana or Prometheus? There are other profiles like Agonis as well, which is an open source project which offers similar features. Now let's get started and see what steps we need to take. Now, first we deploy the EKS cluster using the EKS CTL tool. That is the EKS cluster that hosts the dedicated game server, which we mentioned in the game architecture diagram. Now, next step is to enable the GitOps profile. Now, what is a GitOps profile? A GitOps profile is something that includes Flux CD as well as the game server specification and monitoring component. Now, Flux is the GitOps operator that manages deployment to maintain cluster state. The monitoring component sends logs to synchronize with the CloudWatch or Elasticsearch. Operational metrics are sent over to Prometheus as well as to the native Kubernetes dashboard. Now let's take a look at the game server specifications.
Thanks, Neelam. Now let's talk about how game specification look like, because essentially we need to take all the artifacts that we discussed, that Neelam described, and we need to reconcile the two, and that's what the game spec means, right? In this game, in this spec, you will see all kinds of interesting things about how we want to deploy the game, right? So for example, Neelam was describing the star.py and the star.shell file. So here we tell basically the platform, hey, when you get the image and you want to start things up, this is the execution. These are the commands that you need to do, right? And another point is that you can specify what is the limitation of the how much CPU, how much memory you want to allocate for each game server. And finally, you can specify all kinds of metrics that related to the way that you are deploying the game server. For example, in this example, we are saying, hey, keep 10 instances, 10 game server healthy all the time, no matter what. And we're going to see how the rolling updates are behaving in action. So we said that we specify to the platform, to Kubernetes, hey, this is where you need to take the image, this is what you need to execute, and more specifically about star.py. And now let's talk about the example of star.py. And again, this is just a broad example. It's an opinionated way with regards to the implementation of the specific game, but that can be tweaked to anything that you want and need. So we're going to start with basically what are we going to do when things going to need to be terminated, and that's basically done through the signal, the unit signal sig term. And as you could see, that the first thing is to register a signal handler for sig term. Now the reason that it's important is because that you might want to cascade a message to the game so the game can take action. So for example, if you are using spot instances or things, or the instance that you run needs to be shut down, you're gonna get a signal. The container is gonna get a signal, and basically this signal can be captured by the game, and the game developer can track this change and pop up a message to the player that the game is going to be interrupted. This is just an example of a graceful termination. Now, the second part is, now that we are running on, we want to stack multiple game server on the same instance, right? Because we don't want to use any network overlay. Then we need to allocate new ports for every game server. So we need to have some implementation of random ports. And this is just a way to do it. I'm sure that there are many other ways. In this example, in the get run port, we're going to issue a socket on port 0, and basically issuing port 0 will give us a socket that uses a port from the ephemeral port range. We're going to capture this port, we're going to close the socket, and then we're going to pass it as an environment variable to the star.shell script. Now, if you think about it, the star.shell script is the script that was used by the developers. So what you could see here is that there is a clear delineation between what the developer provided for his for their development process, and we are basically utilizing it, and we are we're not requiring any change specific to the things that was done when it left the CI pipeline. Now let's see this thing in action. As I promised you, we ought to first look at the changes that we did before, right? And as you can see here, this is the change, the last change that I did, and it finished 11 minutes ago, and it took 5 minutes as I mentioned. And we're gonna go, and basically you could see the same thing that I showed you, right? There was only the thing we pushed only the change that was done, just the file that we touched upon, and the rest of the layers are stated as no op, okay, as no operations, and basically we were able to save the time. Now let's look at our cluster now. So I'm going to clear this one because this is our cluster. So we're going to look at kubectl. We're going to just look at what's going on here. As you could see, we have, remember that I told you that we, in our example, we said that we want to have 10 instances that are running. As you can see here, last time I executed this thing was 10 days ago, and they are all running and happy, no restarts and all that, right? So let me just keep this thing running all the time. So we're gonna see the change in action. And here I'm going to show you the repository of the CD. Remember that we are going to have two separate Git repository. The first one will be the repository that describes the continuous integration. That's what we described before in the CI demo. And here we're going to have another Git repository that basically describes the state of the cluster, right? So it holds a configuration. So remember, we made a change that was that basically the main artifact was a new image with the image tag 11. Let me just show you that before I'm jumping all the way. So we are seeing here, and as you can see here, this is running the command with the image tag, and this is the image that was sent, right? So the file is, to change it, will be in the base game server YAML, and I'm going to just jump to this thing, right? And I'm going to modify it to 10, and gonna do git add base game server.yaml, and I'm going to commit the change. I'm gonna say that, and this is going to be the release note, set quality to auto git push, and I'm going to push the change. Now, from that point, once that I made the change, the flux operator that Nilam discussed supposed to sense the change. And what does it mean? It basically runs on your cluster and continuously probing the Git repository that you enable. And here you go. You could see it in action, right? As you could see, you still have the 10 instances that we asked that to run in a running state. And while this is in running state, Kubernetes is creating the containers that are required to take over, right? Now, this is going to take some time, but the interesting part here is that when we told Kubernetes to maintain this deployment, we asked it to keep 10 instances running all the time, no matter what version, because this was the SLA that we wanted to establish to maintain the capacity that we need, that the matchmaking process servers needed based on some capacity requirements, or it can be set as an automatic, as an auto-scale process. Now, as you could see, that as we get new running containers that are 71 second old, the old versions are in terminating state. Now, the reason that they are in terminating state and not terminated at all is because that we told Kubernetes to set some sort of a grace period, and in our example it was 30 seconds just for the demo perspective, but you can set it up as much as you want. So basically, once that we have new instances coming up, we allow the grace period to elapse, and once that the grace period elapses, you will see the instances that are in terminating process going to fade away, and basically the new version of the running instances, the young one, will take over. And you could see that thing in action. Okay, so now we are in a fully updated cluster. Okay. Oops. Okay. So what we saw now, we saw how we control, how we take a Git repository and a Git and a cluster, an EKS cluster, a Kubernetes cluster, and we were able to show you how do we maintain and doing rolling updates. But what if you want to scale out, right? Once that you, let's say that you reach out the capacity of your cluster, or simply you want to make your game available for people in other geographies, right? Because of the latency and other consideration. So how would you scale out this model? Now it is very simple, because we're going to follow the same the Git branch approach, where we are going to provision cluster in the same way that we provisioned, as Nilam showed you in the previous slides, but also for each cluster, for each region, or whatever the construct that you want to use, we're going to create another branch, right? And as you could see here, we just created, we had the cluster in Oregon, and we created two more clusters, one in Dublin and one in Sao Paulo. And we duplicate, basically, we duplicate the branch into the branch of US West, and we duplicate it to two other branches, and basically made the changes in those branches just for the sake of the specific region. Now, the way that we like to do it in Kubernetes is basically to create a config map. I'm not going to go into details about how to do it here, but we're going to publish in the resource page a code sample that will show you how to do it, that will show an example on how to do it specifically. Now, so if you think about what we did both in the CI process and the CD process, the tools that we used in order to induce this change was just git push and git and just git command, right? So the reason that it's so powerful is, if we're going back to the first slides that we discussed, that we presented you, is that simplicity of applying this type of CI and CD, right? You want to, from security perspective, to have as less as possible people that are touching the cluster and knowing, and sometimes they don't know those tools. And also from security perspective, you don't have, if you want to set a permission to an individual or a team member, new team member, all you need to do is to do it through the same process that you would use to set the Git registry permissions. Okay, so let's wrap all this thing into one big picture. So remember this slide. This was the blueprint that Nilam started this presentation. We started with the game artifact. We aggregate those in a way that we are building it and integrating it with the help of the code build. All this thing was orchestrated with code pipeline that pushed the image to the Amazon Elastic Container Registry, ECR. And from that, we had the GitOps operator that was listening to all kinds of changes that happen on the GitOps repository. And once the change was done, it pushed the change in a graceful way through the SLA that we describe in the deployment, and eventually had the player play the most updated and funnest game. So key takeaways, the key takeaways that we have here, we were able to show you how to basically use CI/CD in order to increase the game feature velocity. And we also showed you how we streamline the game operation. Think about all the station that we demonstrated from the time that the developer finished all the way to the part where a player actually played the game. And the last thing is that that this process is consistent and standardized workflow. And why it is important? It is important because that you might want to have another game, right? And you don't have to have a snowflake operations for each game and create all kinds of runbook and playbook for different games. So that's the consistency. Well, that's what we have for you today. Thank you. Please explore the other talks and demos in today's event. And if you have additional questions, please stop by the Ask an Expert section and speak with AWS technical expert. And for more details, we're going to have the demo link presented for you, and check out that in the resource center. Thank you very much.